Dental materials in the oral environment. From this chapter, the reader will appreciate the environment within which dental materials are designed to function, understand the common presentations of dental materials, appreciate the pitfalls of the manipulation of dental materials in the clinic by the dental team, and the significance of these on material performance. Understand how the presentation of materials has evolved to reduce such operator variability. Understand how the presentation of materials has evolved to reduce such operator variability. Introduction. Perhaps surprisingly, when considering their diversity, the materials that are used across the various branches of dentistry have much in common. They are conceived, developed, tested, manufactured, and marketed in the same way by only a small group of dental material manufacturing companies. When they arrive in the clinic, they are kept in the same storeroom. When required for use, they are mixed and manipulated by the dental team in similar ways as they are available in only a small number of presentations. Unfortunately, incorrect handling during this phase could compromise their properties on subsequent placement into the mouth, and in some cases they may be ruined. Dental materials may set chemically, or the setting may be initiated by light, energy, or a combination of both. They are subjected to the hostile environment which is the human mouth, where they are asked to endure similar stresses and strains during function. With all things being equal, their lifespan does not vary significantly either. The first section of this book, consisting of 5 chapters, discusses these general principles and the commonalities between the different material groups. This chapter describes the oral environment into which a material is placed. Failure of the clinician to understand the conditions in which a material is expected to perform may lead to incorrect material selection, which will surely compromise clinical success. Failure of the clinician to understand the conditions in which a material is expected to perform may lead to incorrect material selection, which will surely compromise clinical success. The way in which the material is presented and handled by chairside dental staff will influence its properties in order to minimize operator error. Manufac- Manufacturers have developed less technique-sensitive presentations. Chapter 2 examines how the dental team may influence success by considering clinical factors such as the importance of moisture control when using materials which may be damaged by exposure to water prior to their complete setting. The invention and extensive use in modern dentistry of setting dental materials by exposure to light energy extends across material types. However, this useful technique has the potential to be compromised by various factors, and the dentist must be aware of the potential pitfalls. It is an important criterion that it is undesirable for any dental material to interact with the host, that is, dental patient. Chapter 3 and 4 deal with the biological considerations of dental materials and how potential interactions may be minimized by the manufacturers and dental team. Clearly, all materials must be fit for purpose and conform to various safety, legal, and quality standards. Prior to their launch to market, all dental materials are tested extensively. It is desirable that the end user, the dentist, understands which laboratory tests each material has been subjected to and how relevant this may be clinically. Often promotional and technical literature may be difficult to interpret, yet it is vital that the dentist is equipped to understand this information. By understanding why certain chemicals are contained in the materials, it may be possible to make an educated assessment as to how the material is likely to behave with respect to handling and function. This will enable the clinician to make informed decisions as to whether a particular material is suitable for a given situation. Lastly, Chapter 5 discusses how materials may be stored and managed in a clinic or dental practice prior to use. Storage in the correct manner will ensure that the material reaches the dentist in optimum condition. The hostile oral environment. When dental materials are placed in the mouth, they enter a very hostile environment. In fact, they are asked to perform and survive in conditions more extreme than those found on the oil platforms in the North Sea. There are numerous microorganisms in the oral cavity, and many bacteria produce acids as byproduct of their metabolism. This has the effect of lowering the intraoral pH. Ingested foodstuffs and liquids can also rapidly change the pH of the mouth, swinging between mildly alkaline and strongly acidic. Saliva plays a role as a protective fluid barrier by acting as a buffer. However, some of the constituents of saliva, such as acids and organic fluids, can cause degradation of the dental restoration with time by reacting with it chemically. During function, restorative materials may well be subjected to intermittent loading and unloading. This is cyclical loading. The material will have to resist this mechanical loading. The magnitude and direction of which contributes to stresses and strains within the material and the tooth structure supporting it. Furthermore, the material may be subjected to a variety of fluids. Furthermore, the material may be subjected to a variety of fluids at varying temperatures during the course of a day, ranging from freezing to 60 degrees centigrade. This is called thermal cycling. pH stands for the power of the hydrogen ion and is a measure of the acidity or basicity of a solution. It ranges from 0.1 highly acidic to 14 highly alkaline, with pH 7 being neutral. Buffer solution: an aqueous solution in which the change in pH of the solution is limited. When a small amount of acid or base is added to it. An aqueous solution in which the change in pH of the solution is limited. When a small amount of acid or base is added to it. Buffer solutions are used as a means of maintaining pH at a nearly constant value. Dental restoration: a form composed of a dental material designed to restore both form and function of dental hard tissue. Stress: measure of the intensity or internal distribution of the total internal forces acting within a deformable body. Stress is measured in newtons per meter squares. Strain: the change in the dimension of a material per unit length when an external force is applied to it. The combination of these chemical, mechanical, and thermal challenges is often synergistic. It is therefore obvious that over long periods of clinical use, the effects of these challenges will profoundly influence a material's behavior and therefore a restoration's performance and longevity. The influence of the presentation of materials on success. Unfortunately, the harsh oral environment is not the only hazard which can influence material performance. In many cases, the material may not be supplied in a controlled and metered form by the manufacturer. Instead, the dental nurse or dentist must mix the components supplied by the manufacturer just prior to the placement of the material in the mouth. This means that the manufacturer may have only a limited influence over the final state of the material being used clinically. This is problematic, as failure to correctly manipulate the constituents can have a major influence in the failure of the material to perform as expected. This potential for error by the end user, that is, the dental team, is very high. To minimize these types of error and maximize clinical success, dental material manufacturers have evolved a range of material presentations to minimize the risk of mishandling. An example of this is the reduction in the use of powder and liquid formulations in favor of ready-mixed pastes which only require to be light cured. These presentations optimize both the proportioning of the ingredients and the mixing of the materials. Powder and liquid presentations: as the name suggests, these materials, usually cements, are provided as components which the user must mix and place at the site of use. This presents a number of problems. Firstly, the proportions of each component should ideally be similar, as it is often difficult to mix a much smaller volume of one with a large volume of the second and still ensure even distribution of the two components. Firstly, the proportions of each component should ideally be similar, as it is often difficult to mix a much smaller volume of one with a large volume of the second and still ensure even distribution of the two components. Secondly, the components need to be dispensed in a manner that ensures that the correct proportion of each component is metered out. It is also important that the proportions do not require too much precision, as the dispensation process in the clinic is fraught with problems. Dispensation of powder is subject to considerable variability. During storage, undisturbed powder in a bottle or tub for a period of time will settle and compact. It is important that the powder is fluffed by shaking the container so that the correct amount of powder is dispensed. Failure to do this will mean that more powder is dispensed, thus affecting the powder to liquid ratio. Always shake the bottle or tub before dispensing the powder. This fluffs the powder so that the correct amount is dispensed and mixes the contents thoroughly, as these materials frequently contain mixtures of different powder compositions. A bottle of glass ionomer cement, Chemfill Superior, Dentsply, and a tub of alginate impression material, Blueprint Dentsply, being shaken by the dental nurse to ensure the correct dispensation of the powder. Powder versus granules. The ease with which the solute dissolves affects the rate of reaction. Generally speaking, dental cements are presented in either powder or, in the case of newer materials, granular form. A powder is a fine precipitate produced by grinding or milling small particles. The finer the particle, the more rapid the initiation of the chemical reaction as the surface area to volume ratio increases. Granules are larger agglomerates of semi-fused particles with a porous structure, which facilitates the permeability of a liquid into the agglomerated mass, and the surface area available is greater for reaction. This is a similar presentation to the popular coffee granules found in some instant coffees. Figure 1.4 shows the granular and powder presentations of instant coffee. The granular variety was introduced to improve the rapidity with which the coffee may dissolve when hot water is added to it. Figure 1.2a and b, a scanning electron micrograph and pictorial representation of a conventional glass ionomer powder. This illustrates the considerable range in particle sizes in a cement. This can influence the rate of set of the material. A scanning electron micrograph and pictorial representation of a granular glass ionomer powder. Figure 1.4, the coffee powder on the left has a granular presentation whilst the other is ground powder coffee. Note the difference in appearance of the two samples. Solute is a solid which dissolves in a liquid. Rate of reaction. When mixing the ingredients, it is important to realize that as soon as the constituents are brought together, then the setting reaction commences. Many manufacturers incorporate a retarder into the solute to prevent the setting phase commencing immediately, so slowing the reaction initially. This has the effect of increasing the working time, but there is still a fixed amount of time during which mixing and placement of the material can take place. Once this time has been exceeded, the setting phase will commence. Figure 1.5. Increase in viscosity of mixed material and time. The change in viscosity of two cements. At the beginning of mixing, the viscosity of the paste is low. This viscosity remains the same for 1.5 minutes with the express set material and 2.25 minutes for the regular cement. After this time the cement begins to set and thicken and the viscosity decreases. Once the cement has set, the viscosity is the same again. It is desirable to have a long working time and short setting time, but this is not possible because once the chemical reaction has been initiated, the setting reaction accelerates until the reactive components are exhausted. Working time is the time between the commencement of mix and the first indication of setting. Setting time is the time from the commencement of mixing to the time at which the material has set clinically. Effect of temperature and humidity. The temperature and humidity of the clinic or laboratory during the mixing and setting phases will influence the rate of reaction. In general, any increase in temperature above ambient will lead to an acceleration of the setting reaction. This can have considerable significance in a clinic which does not have a controlled temperature. On a cold day, the material will have a longer working time, while on a hot and humid day the material will begin to set prematurely. It is often advisable to store susceptible materials in a refrigerator, the effect of which will be to increase mixing and working time. However, this can create problems. Water-based cements have an optimum level of water to achieve their best performance. If the slab on which they are mixed is cooled to a temperature which is below the dew point, Figure 1.6, once the slab is back at room temperature, condensation of water from the atmosphere will lead to beads of moisture on the surface, which will then be incorporated into the mix, thus reducing the powder to liquid ratio and producing a weakened cement. This can be overcome by using paper mixing pads. However, these pads are unsuitable for mixing of stiff, highly viscous acid-base cements as the paper curls at the edges as the material is spatulated. Drops of water condensing on a chilled glass slab. Incorporation of this water into a powder-liquid mix will alter the ratio, so affecting the final properties of the cement. It is important to remember that the temperature of the oral cavity is generally between 10 and 14 degrees centigrade above that of the clinic. Once a material is placed in the mouth, the setting rate will be increased substantially. Dew point is the temperature that air must be cooled for water vapor to condense into water. Viscosity is the resistance of a liquid to flow. Clinical implications of the setting phase. To achieve the optimal properties of the material, it should not be disturbed during the setting phase. Manipulation of the material during this phase will have long-term deleterious deleterious consequences. Restorative materials must be maintained in a steady state during the period between the end of the working time and the completion of set. Failure to do this will lead to the material being stressed and weakened, so impairing its clinical performance and longevity. For example, in the case of elastomeric impression materials, such as silicone rubbers, if they are disturbed during the cross-linking phase, they will stress relax on removal from the mouth. This leads to distortion resulting in the cast restoration failing to fit. The impression tray should be evenly supported during the setting phase. The reliance on the patient to support the tray or leaving the tray unsupported is likely to lead to deformation of the impression. Elastomer is a material which has elastic properties, allowing it to recover to its original shape after distortion. Cross-linking is covalent or ionic bonds that link one polymer chain to another to form a solid structure. Stress relaxation, the phenomenon of a material under stress to return to its unstressed original form once any restraint is removed. Impression material is a material used to record the shape of the structure in the mouth so that a model may be constructed. Impression tray is a prefabricated U-shaped carrying device which supports the fluid impression material. Cast restoration is restoration produced external to the mouth and cemented into place. Evolution of material presentations. The traditional powder-liquid cement system is the presentation most likely to result in most significant user variability as already discussed. If the components of the material can be delivered to the dental team in the correct proportions and in such a way that minimal or no mixing is required, then the risk of operator-induced variability can be reduced or even largely eliminated. A number of currently available presentations address these problems, namely capsules, compules, automated paste delivery systems. Encapsulation: a capsule is a container that holds the active ingredients of a material in separate compartments until activation. It then becomes the mixing chamber. The activated capsule is then placed into a mechanical mixing machine to blend the components of the material together. Manufacturers have designed capsules that allow powders and liquids to be mixed in the correct proportions to achieve the desired mix and consistency. Figure 1.8 shows the design of a capsule and its contents. Figure 1.7a and b examples of capsule. The one on the left is manufactured by 3M ESPE and contains resin-modified glass ionomer cement, Potac fill, and the other is Chemfill Supreme Dense Ply, a glass ionomer cement. Note the black plastic of the Potac-fill capsule protects the constituents from ambient light as this material is light-activated. Figure 1.A-B. Assembled and exploded capsule components. Note the access hole to the main chamber and the pillow which lies over this. Note the access hole to the main chamber and the pillow which lies over this. The grey cylinder which lies over the end acts as a plunger, forcing the cement out through the nozzle. After mixing it is complete. This is the plastic clip. This is the pillow, this is the access hole, outer casting, plunger, powder. So the assembled and exploded capsule components. Note the access hole to the main chamber and the pillow which lies over this. The grey cylinder which lies over the end acts as a plunger, forcing the cement out through the nozzle after mixing is complete. Most capsules consist of a chamber with a nozzle at one end through which the mixed material may be extruded. The chamber internally is a rounded cylinder with a small hole either on one side or the other, or at one end. The powder is stored in this central chamber. Over the small hole lies an aluminum pillow which contains the liquid. This pillow is covered by a plastic clip. When pressure is applied to the plastic clip, this ruptures the pillow and the liquid is expelled into the chamber containing the metered amount of powder. Alternative systems have the liquid in a pillow at the opposite end from the nozzle and are activated by a half turn of the bung. Some encapsulated glass ionomer cements require the capsule being bung to be twisted through 180 degrees prior to syringing. Failure to do this will result in no material being dispensed from the capsule as the nozzle is occluded, forcing the outer casting of the capsule apart. Figure 1.9. Failure to twist the capsule prior to dispensation has resulted in no material being expressed from the capsule and the capsule rupturing under the pressure being applied to it by the syringe driver. When using capsules containing ingredients for a cement or restorative which require activation, the dental nurse should ensure that pressure is applied to the clip for a period of time long enough to expel all the liquid into the chamber. The liquid is frequently rather viscous and a minimum time for pressure to be applied is 2 seconds. Figure 1.10. Failure to expel all the liquid will adversely affect the powder to liquid ratio and may lead to difficulties in expelling the mixed material through the syringe nozzle. Pressure being applied to the activator device for 2 seconds so that all of the liquid is expressed from the pillow into the mixing chamber. The powder in capsules will compact on storage with the compacted powder settling at the end of the capsule near the exit nozzle. It is therefore important to always shake the capsule prior to use. Failure to do so will result in a puff of unmixed powder being expressed first, which may interfere with clinical placement. Once the powder and liquid are in the mixing chamber, the capsule is placed in a mechanical mixer. This machine agitates the capsule for a fixed period of time as recommended by the manufacturer, and the mixed material is then extruded into the cavity. Dental amalgam is presented in capsules, but in this case the capsule is used solely for mixing the alloy powder and mercury. The mercury is stored in a pillow which is within the body of the capsule. This is ruptured by the movement of the high-density mercury once mixing commences. Once mixed, the material is placed in a dispensing dish to be picked up and inserted into the cavity using an amalgam gun. An amalgam gun is a carrier device used to inject unset amalgam into the oral cavity. Mechanical mixers. Mechanical mixers figure 1.1 operate either by rotational or an oscillating figure-of-8 movement of the capsule. The speed is variable and each machine should be provided with mixing times for each encapsulated material. The reason for this is the throw of the mixing arm of each manufacturer varies as does the speed of oscillation. The reason for this is the throw of the mixing arm of each manufacturer varies as does the speed of oscillation. This imparts a different amount of energy during the mixing process. The movement of the powder and liquid within the capsule allows the surfaces of the particles to be wetted and the chemical reaction to commence. The movement of the mass within the mixing chamber generates heat, the amount being dependent on the mass of the components involved. At the end of mixing, a paste of uniform consistency should be obtained. Figure 1.1, a mixing machine with a rotary mixing motion. 3MESPE Rotomix, and B, another mixing machine that utilizes a figure-of-8 motion. SDS KERR 4000. Wetting is the ability of a liquid to maintain contact with a solid surface due to intermolecular interactions when they are in close proximity. Limitation of capsules. Even though the proportioning of the components is carried out by the manufacturer under standardized conditions, it is difficult to provide a metered dose precisely. This is because the powders are usually delivered by a hopper, and there is some variation in the amount dispensed as the hopper empties. The filling of the pillow has a similar problem as the metering of small volumes of liquid produces some variation. Variations in the portioning of either the powder or liquid will affect the liquid-powder ratio and therefore the properties of the mixed material. The most significant disadvantage of capsule mixes is in those cases where the material is injected via a nozzle to the side. Here the diameter of the orifice of the nozzle will influence the powder-to-liquid ratio. Too high a powder-to-liquid ratio will make the material difficult to extrude via a small nozzle, which may indeed be the most appropriate for delivery. It is important that the correct mixing time is adhered to. Too short a time will lead to an incoherent mass with the powder and liquid inadequately mixed. Too long a mixing time will reduce working time and accelerate set. Compules. A compule is a small cylindrical container with a delivery tip and plunger. They are also sometimes referred to by some manufacturers as tips or cavifills. Ivoclar Vivadent. An example of a product presented in compule form is shown in figure 1.12. Compules have been designed to deliver materials where all the active ingredients have already been mixed together by the manufacturer into an injectable paste. This reduces the risk of incorrect mixing and produces a material almost free of air voids. As such, those materials suitable for use in compules are limited to polymer systems activated by light. Compules containing a resin-based composite Miris to coltan weldant. Polymer are large molecules composed of repeating structural units typically connected by covalent chemical bonds. During the manufacturing process, the material is loaded into the compule chamber in paste form, and then a plastic plunger is inserted on top and driven down a fixed distance. Figure 1.13. The process is usually carried out in an environment illuminated by amber light so the material will not be set prematurely. This ensures that the material is packed firmly into the base of the compule and up to the nozzle. The cap covering the nozzle is then placed. The light-resistant material forming the compule walls provides protection from ambient light so preventing premature polymerization. Dispensation is achieved by inserting the compule into a gun, which is designed to drive the plunger further into the compule chamber, extruding the material via the nozzle for direct placement into the cavity being restored. The nozzle diameter varies with the viscosity of the material. The thicker the paste, the wider the nozzle. Figure 1.14. Figure 1.13. A dismantled compule demonstrating its components. Figure 1.14. Two compules with different nozzle sizes. The wider one permits the extrusion of a regular viscosity resin composite material, Maris to coltan weldant, and the narrower one, a flowable resin composite material, Explo Dentsply. Some materials are so viscous that they cannot be delivered from compules but are only supplied in a syringe presentation, for example P63MESPE, figure 1.15. The use of a syringe can result in the material being affected by the ambient clinic lighting as the material is not delivered directly to the cavity. Figure 1.15. P63MESPE, a packable resin composite material, is so viscous it is only supplied in the syringe form. Note the wide bore size. The compule is placed into a gun for ease of delivery, and Figure 1.16 illustrates two examples from the range of guns available. Most work on the single lever delivery of the plunger. This can result in the plunger not passing horizontally down the internal surface of the compule, so an erratic injection rate occurs. To overcome this shortcoming, another more sophisticated form of gun is available whose plunger is driven down the barrel of the compule centrally and evenly. Two examples of guns used to express material from compules: single lever delivery gun. B is gun configured to permit plunger to be delivered centrally on capsule plunger. After the paste has been injected into the cavity, it is activated by an external energy source such as a light polymerizing unit. The mechanism of light curing is explained in detail in Chapter 2. Limitations of compules: Compules are considered to be a unit dose and should not be reused. This means that inevitably some material is wasted as not all of the material will be required to fill the cavity. Similarly, there may be a small volume of the material that cannot be expelled out of the compule tip. This is reduced to a minimum by the conical shape of the plunger, which will push the bulk of the material into the nozzle. However, the remaining amount is very small in comparison with the amount frequently wasted when materials are dispensed from a syringe and left unused on a mixing pad. Automated paste delivery systems. When it is not possible to put all the active ingredients together in one paste, alternative systems have been developed. Figure 1.17. Here the two pastes are presented in double-barrel syringes, and by applying force to a lever, unit doses of the two pastes may be dispensed onto a mixing pad for manual mixing. The advantage of this delivery presentation is that the pastes are delivered in the correct proportions to one another, and it obviates the proportion estimation carried out by the dental nurse from two individual tubes. A more accurate mix is therefore achieved. Figure 1.18. Different material types are now available in this presentation. Two automated paste delivery systems, 3M ESPE's clicker system illustrated by Vitribond Plus, and GC's paste park dispenser illustrated by Fuji Lining LC. Figure 1.18 A to D. The dispensation of two pastes using the clicker device. Dispenser 3MESPE. The pastes are released as the clicker lever is depressed. Full depression of the lever ends the delivery. Figure 1.19. Four different materials presented in 3MESPE's clicker delivery system from top to bottom: a resin-modified glass ionomer luting cement, self-etching dual-cured resin composite, a resin-modified glass ionomer lining cement, and a dual-cured resin composite adhesive. A dual-cured resin composite adhesive. Cartridges. A subgroup of automated paste delivery systems consists of cartridges. Their main indication is for mixing two semi-viscous pastes where a large volume is required, such as impression materials or materials specifically designed for temporary placement of tooth structure removed during crown preparation. Cartridges are designed to permit two pastes to be mixed in ratios of 1:1 up to 1:10. Figure 1.20. A spiral delivery tube is needed to mix the material. Figure 1.21. The number of helical turns depends on the material's viscosity. The more viscous the material, the fewer helical turns are available to thoroughly blend the two pastes together. The two constituent pastes are injected down the spiral and slowly blend together, allowing the mixed paste to be extruded at the site of use. A larger scale variant of this design is the mechanical impression material mixer, which dispenses the material directly into an impression tray. Figure 1.22. Figure 1.20. A cartridge mixing system. ProTem For 3MESPE, the difference in the ratio of paste and catalyst is determined by the differing size of the two tubes. In this case, the ratio of the two pastes is 4:1. Figure 1.21. Three mixing and delivery nozzles with different diameters. Note the differences in numbers of turns in the helix. The smaller the number, the more viscous the material. Pentamix 3 3MESPE impression material dispensing machine. The two reservoirs of pastes, note the different sizes as the proportions are 4:1. The material is being mixed in the helix of the mixing nozzle. The material is being expressed into the impression tray. As has been discussed earlier, the mouth is a hostile environment in which materials are asked to survive. For a material to perform satisfactorily in this environment, its properties must be optimized. In order to achieve this, modern presentations of materials provide a means of standardizing proportions of constituents and quality of mixing. In order to achieve this, modern presentations of materials provide a means of standardizing proportions of constituents and quality of mixing. In order to achieve this, modern preparations of materials provide a means of standardizing proportions of constituents and quality of mixing. This overcomes the variability associated with hand mixing and proportioning which was commonplace previously. However, as will become apparent in the following chapters, there are other variables that impact on a material during use and which may have significantly detrimental effects on the performance of dental materials. Summary: the mouth is an extremely hostile environment. Materials need to be optimized to achieve their properties. Presentations are now designed to deliver materials as closely matched in performance to that tested in the manufacturer's laboratories to minimize operator mishandling. Self-assessment questions: what environment factors found in the mouth will affect the performance of a dental restorative material? What are the problems with presenting materials in a powder-liquid form for hand mixing? What are the advantages of using pre-dispensed materials in the clinic? Are there any disadvantages? What factors should be considered in establishing the clinical environment?